Hi, I'm Ani Patel. I'm a professor of psychology at Tufts University, and today I want to talk to you about how we can use math to study kind of an interesting idea about music. In fact, it sort of sounds like a crazy idea about music, although it's been around for a while. Actually, it's been around for over 60 years, and it's been suggested by multiple people, including musicologists, so people who study the history of music, by linguists, people who study language and its structure. And the idea is that instrumental music can reflect the rhythm and melody of a composer's native language. So purely instrumental music, music without words, can somehow sound like spoken French or sound like British English. And this is an idea that's been circulated for a while. Part of what makes Debussy's French piano music sound so French is that it sounds like French speech. Part of what makes Elgar's symphonies sound so very English is that they sound like British English speech. I mean, it's a kind of a provocative idea, right? Because no one would ever confuse the sound of pianos with the sound of people talking, or the sound of a symphony with the sound of a conversation. So you would be in good company if you were skeptical about this idea. But what I want to tell you about today is how we can use math to actually turn that idea into something that we can study, and in the end, actually find evidence for it. So it's a way that we can connect math, music, and science. But let me give you an example, a quote of this kind of provocative claim. This comes from a music performer, Ralph Kirkpatrick. He was a harpsichordist and a music scholar. And he said, "Both Couperin and Rameau, like Fauré and Debussy, are thoroughly conditioned by the nuances and inflections of spoken French. On no Western music has the influence of language been stronger." So this is quoted in a book about Western music history called The Tradition of Western Music by Gerald Abraham. And so here is a harpsichordist who's been playing French music for a very long time and is very knowledgeable about it, saying that something about that music just is soaked in the sound of the language. So that's just one example. I'd actually like to play you a couple of clips of music to give you an idea of the kinds of music people are thinking about when they make these sorts of claims. I'll start with a clip of French music. This is a clip from Debussy. That's from Debussy's La Mer, and I don't think it sounded at all like speech. Here is from an Elgar symphony. Now that's an English composer. Debussy is French, obviously, and Elgar's English. In fact, many of you have heard Elgar's music. His most famous piece in our culture is Pomp and Circumstance, which is the music that many people graduate to at high school or college. So that just gives you an idea of the kinds of music they were talking about. So clearly, didn't sound like language at all, so how could that possibly reflect the rhythms and melodies of speech? The first claim that I know of that was published is from the 1950s. That was from a linguist named Robert Hall, who wrote a wonderful 2-page essay called Elgar and the Intonation of British English. So how can we use science to test that idea? So, where would we even begin? Well, first thing we need to do, obviously, is find a way to measure rhythm, because we're going to focus on rhythm in this talk. Find a way to measure rhythm, and in a way that allows us to compare music and speech numerically with numbers, because numbers are the language of science. So we need some kind of method for measuring rhythm. And we can start small. That's a common strategy in science. So instead of saying, we're going to see if we can prove this for all music in all times in all cultures, that's way too big. We can say, let's start with just a couple of cultures and see if we can make any headway. And so that's what we did. We focused on English and French because those are cultures that often come up when people make these claims. But when you start small, you still have big goals. So what we wanted to do was develop a method that could be applied to other cultures in other historical times. And that's actually what's happened since our work. And English and French are actually a good choice to start with because linguists agree that they have very different speech rhythms. So if you're going to look for cultures where the music rhythm differs and reflects the speech rhythm, English and French, British English and Continental French is a good place to start. Before you can even start to go down that path, you have to ask, what is rhythm in speech to begin with? What does that mean that speech has rhythm? For many people, the very term rhythm suggests some kind of periodicity, like a metronome, something that repeats regularly in time. That's okay, but it's kind of too narrow concept of rhythm for language, because language doesn't have a regular beat. You don't tap your foot to speech or dance to ordinary speech, and we're talking here about ordinary speech, not language or poetry. All these claims about rhythm in the music reflecting the language are talking about ordinary day-to-day spoken language. But linguists will tell you that languages have rhythms. even though they don't have any kind of beat. So what do they mean by that? They mean some kind of systematic pattern in the timing or the accent of the language that clearly gives that language a certain rhythmic feel. So let me give you one example using English and French. So a very important aspect of English speech rhythm is that two-syllable words have a very strong bias to have the accent or stress on the first syllable. What does that mean? Well, when we say words in English, even if we're not putting any special emphasis on part of the word just naturally has more emphasis or stress on one syllable than the other. So in English we say taxi, we don't say taxi, and we say driver, we don't say driver. So we say, I need a taxi driver, not I need a taxi driver, right? That would not sound like a native English speaker if I spoke in that way. Well, it turns out that French has exactly the opposite bias, that in many two-syllable words, in context, the prominence is on the second syllable. So think of merci beaucoup. Those words have more emphasis on the end of the word than the beginning. We don't say merci beaucoup. You would sound like an American tourist if you talk like that. So there's this very systematic difference in the way accent is placed in words, and that's part of the rhythm of the language. If you don't know that as a speaker and you put the accent on the wrong syllable, you'll definitely be identified as a non-native speaker. So that's an example of rhythm and a difference in rhythm between English and French that has nothing to do with beat or periodicity. There's nothing about a stable, steady beat underlying speech that has anything to do with that rhythmic difference. So that gives you an idea. And that might be an interesting thing to pursue in terms of looking for some kind of reflection of that in instrumental music. But I've never really been able to figure out how you take that difference and look for an analog of it or a mirroring of it in instrumental music. If you think of one, let me know, because I'm really interested in that question. So I'm not going to focus on that accent difference. I'm going to focus on a timing difference. Something about the timing of English and French that's different. And this was discovered sometime in the early 2000s. Not by me, but by other researchers that work on the rhythm of speech. And this timing difference has to do with a particular phenomenon in language that we call vowel reduction. So you know what vowels are, and reduction means, obviously shrinking. And this phenomenon refers to the fact that in some languages, unstressed syllables become very short, and the vowels in them become very kind of neutralized. So let me give you an example. In English, we have the word celebrate. Celebrate has stress on the first syllable. We say celebrate. We don't say celebrate or celebrate. We say celebrate. But when people say that word in ordinary conversation, that's one stressed syllable, cel, and then two unstressed syllables, abrate. But pay attention to that second syllable. When we say it in normal conversation, we don't say celebrate. We don't give that second syllable a full vowel. We say celebrate. That second vowel is very short. It's a little like sound, what linguists call a schwa. And it can be just, very, very short. That's called a reduced vowel. Reduced vowels in these languages are often right next to stressed vowels, like celebrate. So cel is stressed, l is unstressed and reduced. And so that creates a contrast in timing, because those reduced vowels are very short and the stressed vowels tend to be rather long. That's part of how we hear them as stressed. So this phenomenon creates a kind of long-short duration alternation pattern in some languages. But in other languages, like for example French, unstressed vowels don't tend to get reduced very much. So we don't get this sharp contrast between the timing, the duration of more stressed and less stressed vowels. They don't have strong vowel reduction. So, well, what does that mean for rhythm? Well, what that means is when you speak sentences of English or French, English sentences are much more likely to have these sharp contrasts in the duration of vowels from one word to the next. And I can illustrate that for you in a graph that actually shows this using numbers. So let me show you. So in this graph, you see two things. You see a graph on the top with a little squiggly line. And what that line is, each ball in that line, each point, is showing the duration in milliseconds of one vowel in a sentence of English speech. Let's listen to the sentence.
Finding a job is difficult in the present economic climate.
Okay, she said finding a job is difficult in the present economic climate. And if you look at the graph, the first little ball, the first point at about 120 milliseconds, is the duration of the I in finding. And then that next vowel, which is very short, is the duration of the D in finding. And so on, all the way through the sentence. You can just read along, finding a job is difficult. Each vowel's duration is shown there. And what you can see when you look at that graph, it's very jagged. There's some that are really long and some that are really short, and often they're right next to each other. This kind of zigzag pattern of long, short, short, long. The bottom graph shows a sentence of French speech. And I'll play it for you, and then we'll talk about the durations of that sentence.
La reconstruction de la ville a commencé après la mort du roi.
Okay, and so what she's saying is a sentence of French, and each point again is the duration of a vowel. And just looking at the graph, you do see a little bit of this long-short thing going on, but not nearly as much as in the English sentence. The durations are much less jaggedly organized. They're more equal, there's less contrast. So this is of course one sentence from English and one sentence of French, so you can't generalize based on this, but it kind of gives you the idea that maybe there's something about the timing of English sentences that is kind of systematically different from the timing of French sentences in terms of this long-short contrast. Well, that's what linguists kind of latched onto in the early 2000s and said, maybe we can find a way to measure this. It doesn't have anything to do with beat or what they call periodicity, some regular underlying pulse, but it may be a systematic difference. So here's where the science and the math comes in. They developed an equation, a way to measure this and put a number on it. And they gave the equation a name. It's called the Normalized Pairwise Variability Index, but let's just call it the NPVI as a nickname. And we'll be going through that equation in a little bit of detail because that's how they made this discovery and that's how we were able to go on to do our work. This slide kind of gives you an intuition of what this equation is really measuring. Imagine, what you see is some bars on this slide. The top line of bars, there's some long bars and some short bars, and they're kind of alternating, long, short, long, short, long, short. And if you imagine those bars are duration, so a long duration followed by a short duration, and you put those durations as numbers into the NPVI equation, you would get out a high NPVI, meaning that there's a lot of contrast between neighboring durations. Look at that bottom set of bars. It's actually the same set of bars. They've just been reorganized in time. So now all the long bars are together and all the short bars are together. And now there's not much contrast between neighbors. Most neighbors are very similar in duration, except for that one in the middle, one pair. Now the equation, if you feed these in the numbers, you'll get a very low NPVI because there's very little contrast between neighboring durations. So I hope you get the idea that this equation is an equation that gives you a number back that tells you how much duration contrast is there between neighbors in a sequence of durations or numbers. So typically it's a measure of durational contrast, this NPVI. And the nice thing is, since it's just durations you're measuring, you can apply them to any unit. It could be a vowel in speech, a note in music, anything you want. But most linguistic work has focused on vowels. And it's really sensitive to the duration ratio between events. So kind of, is this 3 times the duration of that, or is 1/3 the duration of that? That's essentially sort of what it's measuring. We are often sensitive to ratios. So if I play the same rhythm at different tempi, like take shave and a haircut, right? The famous, I can do that tempo, or I can go slow. And you can recognize it both times. All the durations are different the second time around, but the ratios are similar from one note to the next in terms of how long each one is compared to the next. So now we're going to go through the equation. And this is important because to do this kind of research, you have to kind of get into the math. It's really not that hard. So let's just say, we've gone back to this image of bars and numbers, and let's say these are the numbers that are the durations of these vowels, say. And these are arbitrary numbers, but just to give you an idea, the numbers are 5, 1, 4, 1, 6, 1, 1, 5. And what I'm going to do with you is go through this sequence of durations and compute the NPVI. So how do you do it? Well, the first thing you do, you kind of repeat 3 steps over and over. The first thing you do is you look at the first pair of numbers, which is a 5 and a 1. You take the absolute value of their difference. So 5 minus 1 is 4, but it could have been 1, 5, and then 1 minus 5 would be -4, and the answer would still be 4 because it's an absolute value. Then you take the average of the 2 numbers. So 5, the average of 5 and 1 is 3, because 5 plus 1 divided by 2, take it the average is 3. And then you take the ratio of the difference, which we got computed first, 4, over the average, 3. And 4 over 3 is 1.33. So that is your NPVI score for that first pair of numbers. Then you repeat that process for the second pair of numbers, which is 1 and 4. So let's do that. So first thing we do is get the absolute value of their difference. 1 minus 4 is -3, but the absolute value is 3, so that's our first value. The second thing we do is get their average, which is 1 plus 4 over 2, 2.5. And then we take the difference as the numerator and the average as the denominator. So 3 over 2.5 is 1.2. Okay, and now our difference score, or NPVI score, is 1.2. And that's kind of neat, right? Because the NPVI score for 1.5 or 5.1 was 1.33, and the score for 1,4 is 1.2, which makes sense, because if it's a measure of duration contrast, you want things that have more duration contrast to end up having bigger numbers, and things that have less contrast to have smaller numbers. And 5 and 1 is a bigger contrast than 1 and 4. So I think you get the idea. Let's do one more. Let's do 4, 1. Absolute value 4 minus 1 is 3. The average is 2.5 of 4 and 1, and the ratio is 1.2. Exactly the same contrast number for 4, 1 as we got for 1, 4, which is a good thing because they have the same amount of contrast, right? And you can go right down this, I'll just kind of go down this set of numbers, and you can see if I repeat this process for these pairs, I continue to get numbers that make sense. Here's for 1, 6, I get a contrast score of 1.43 using the equation. That's good, that's the biggest contrast we've seen so far, so that's the biggest number we've got so far. 6, 1, exactly the same number as 1, 6, that's good. 1, 1, contrast score of 0, right? Because there's no difference in duration between 1 and 1. And then 1, 5 gives us 1.33, just like 5, 1 gave us 1.33 at the beginning of the sequence. Okay, so now we have 8 durations, have yielded 7 numerical values, 7 contrast values. So what we do is we take the mean of those contrast values, we average those, we multiply by 100, just as a scaling factor, and we get the NPVI value, which in this case is 113, because the mean of those numbers is 1.13. So that's how you do this math. You basically are looking at one pair of durations at a time, getting a number that says how different they are, and then averaging all those numbers together. So the higher the NPVI, the more average amount of contrast between successive durations. One thing that's important about this equation is that it really only cares about ratios of durations between adjacent numbers. And you can prove that by taking all those original numbers in the sequence that I gave you and multiplying them by 10, like I did in this slide. Now every number is 10 times bigger, but the NPVI doesn't become 10 times bigger. It's actually going to end up being the same because the ratios between adjacent durations is the same. So the ratio of 50 to 10 is the same as the ratio of 5 to 1. And if you do the math, as you see here, by taking the absolute value of the difference, the average, and their ratio, you get exactly the same contrast score, 1.33, for 50 and 10 that we got for 5 and 1. And that'll hold true all the way down the line, and you'll get exactly the same NPVI value at the end for this sequence where all the numbers are 10 times bigger. So this equation really cares about the ratio of durations. All right, one last thing about this equation, then we can go on to actually use it to do some interesting work. You might have heard of things like standard deviation or measures of variability in a sequence, which is just a mathematical measure of how much numbers vary in a sequence. This equation gives you a different answer than those kinds of measures, because this equation cares about the order in which the numbers come in, right? So if we took our original sequence of numbers and computed their NPVI, we get 113. If we compute their standard deviation according to standard statistical mathematical approaches, we get 2.2. And you can look up the formula for standard deviation. It's a very widely used measure of variability. Now let's take those same numbers and rearrange them in the order of those numbers now. And I've done that on this slide, and I've put some of the bigger numbers closer to each other and some of the smaller numbers closer to each other. So now there's not so much contrast in duration between neighbors. The standard deviation is going to end up being exactly the same. It doesn't care what order the numbers come in. It just throws all the numbers into a bag and measures how much they vary. But the NPVI cares a lot. In this case, it's gone down by almost but more than half, I would say, right? Because now there's not as much contrast between adjacent neighbors. All right. So I hope I've given you a sense of how this equation works. And an equation in science is like a tool. If you really understand it and how to use it, you can do all kinds of things with it. Think of all the things you can do with a hammer once you know how to use it. Well, this equation sort of became our hammer for addressing this old and interesting question in musicology. So I'll briefly show you what the equation looks like in math symbols. And when you first look at it on this slide, you can see it looks a little scary. But all it is, all that notation is just a mathematical way of expressing what we just did step by step. And if you take math, you'll learn this is what's called a summation of a series. And those little variables stand for different things. In this case, m is the number of duration values. D sub k is the duration of the kth value. K can be 1, 2, 3, and so on through the equation. And you sum them together after taking the difference between neighbors divided by the average between neighbors, multiply by 100, and divide by the number of contrast values. So Again, this is math that you might look at this initially and think, whoa, I don't want to go anywhere near that. That's too complicated. But if you just try it and work through it, you can see it's not that bad, and it opens up new ways of studying music and math. You can actually prove all this that I've been telling you to yourself. You could enter that equation on a spreadsheet in Excel, or you can go to Google and type in NPVI calculator, where right now there's a calculator online where you can put in values and it'll compute them for you. And it's also part of this equation has now become part of a toolkit for doing work in musicology that's numerical, it's computational, called Music 21. It's free and it's based out of MIT. So if you're interested in mathematical patterns in music, check out Music 21. And there's actually a function in that program called NPVI you can use to compute the NPVI durations of notes. Let's take a step back from the math and think about the big picture for a minute. Why do we care about this equation? It's a way of measuring rhythm, of measuring timing patterns, but it doesn't have anything to do with beat or pulse or underlying metronome-like periodicity, which is good because speech doesn't have that. So how do you do it? How do you actually apply it to speech? And not just one sentence of speech, but a lot of speech. Because when you do science, you want to sample broadly from the thing that you're studying. Well, what scientists did before me, other scientists who worked on language, had already come along and used this equation to study patterns of duration in the timing of sentences in English and French and other languages. So they used sentences like these, ordinary news-like sentences that people would read aloud, like the local train left the station more than 5 minutes ago in English, or an ordinary news-like French sentence. Some are written on this slide. They would get native speakers to say the sentences, they would record them, and then use computers to measure the durations of their vowels, and then put those durations into the NPVI equation and measure how much duration contrast there was between vowels in sentences. You get one NPVI score for each sentence telling you how much contrast there was in that sentence. And let me show you some results from that kind of work. This is a graph that shows some results of this kind of research when they measured English speech, many sentences from many speakers, versus French speech, also many sentences from many speakers. And what you see is a mean value, that's the circle, and a little standard error value above and below, which is a measure of how much that value varies. And you can see a big difference. English has a lot more of this contrast in its sentences than French does. And so another way of saying this is, if you're into musical kind of terminology, is that English speech kind of swings more than French speech. It has more of this long, short duration contrast. When we saw that equation and we realized it could be applied to any sequence of numbers, we thought, okay, well, to some extent, you can think of music and rhythm as a sequence of numbers. In fact, that's exactly what music notation does. It represents music as a sequence of numbers. It uses visual symbols, but underlying those symbols is a certain kind of math. So let me show you a couple of examples. This is a theme from Debussy and a theme from Elgar, taken from a resource book called A Dictionary of Musical Themes. This is music notation, and what I've written beneath each note is the relative duration of each note. So if you know music, you know a quarter note counts as one beat, say, and an eighth note as half a beat, and so on. And you can write down exactly the relative durations of notes, and those then become numbers that you can plug into this equation. So let's actually just listen to these first to give a sense, because what happens with these examples, the reason I picked them, is that the Debussy has a lower NPVI than the Elgar, these two themes, less duration contrast. But let's listen to them, and you can probably just hear that. Okay, here's the Debussy. And a kind of smooth flowing feel. And here's the Elgar. And I hope what you heard in that Elgar was a lot of this sort of long, short, ba-ba, ba-ba, that kind of duration contrast, which gives, of course, the sequence a high NPVI value. And in fact, if you run these numbers through the equation, you find out that this one theme of Elgar has a higher NPVI than the Debussy theme, quite a bit higher. Of course, that's just one theme from one composer from England and France, and so nobody would believe you if you tried to prove this idea with just that little evidence. You have to sample much more broadly. So that's what we did. We took advantage of this wonderful resource called A Dictionary of Musical Themes that was compiled in the 50s, I think, by a couple of musicologists who wanted to kind of write down the most salient themes from well-known pieces of classical music, pieces that have been recorded a lot. And we looked at for composers in this book that had lived around the time of Debussy and Elgar, so born in the 1800s, died in the 1900s. And we got 6 English composers and about 10 French composers. And their names are shown here on this slide, and you might recognize some of them. Holst is a very famous English composer, composed the Planets, for example. Debussy you probably have heard of, but also Ravel, who wrote Bolero. He's in this list on the French side, Camille Saint-Saëns, and so on. So we had about 130, 140 English themes, about 180 French themes from this book, and we just did what I showed you. We turned all those themes into sequences of numbers based on their notation for the duration values. We plugged them into the equation, and we said, is it true that on average, English themes have more of this long-short contrast than French themes, just as English sentences in spoken language have more long-short contrast in their durations than French sentences? And that is what we found. We first reported this in 2003, and I'm showing you a graph which puts it all together. It shows the English speech and French speech values that I showed you before for the NPVI, and now I've added the musical values. And you can see they're different. They're not as different as the speech, but they're different, and they're different in the same way. English has a much higher value than the French value. So that was an exciting finding for us. It was the first kind of empirical evidence that supported this old and somewhat seemingly crazy idea that instrumental music can reflect a composer's native language. This study was replicated by others, which was very gratifying, because when you do something in science and you want to see if it holds true generally, it's good to have other people try it with different materials, and that's been done with this work. For English and French music, I should say. So this finding raised a whole bunch of questions. Some people wondered, well, how would this happen? Why would you ever get this kind of a reflection of speech in music? Some people thought, well, maybe composers are just kind of using folk songs in their melodies. And folk songs they're written with words, and the words have the rhythm of the language built into them. And that's one idea, but we don't think that really explains this result, because composers like Debussy and Elgar aren't typically thought of as borrowing a lot of folk music in their compositions. So we think this is actually telling us something about the mind. That when you learn a language, part of what you learn is not just the words and the grammar and so on. You actually learn the rhythm and the timing of the language and how to use it. And people are aware of how good you are at that. Very subtle differences in your timing can indicate that you're not a native speaker of that language. So that's all part of learning a language, learning to speak fluently. It's learning the right rhythm with which to speak. Everybody has that in their heads as a native speaker, and we think composers, being very sensitive to sound, can draw on those kinds of patterns when they compose. It doesn't even have to be consciously, it could be subconsciously. So what can we conclude from this line of work? Well, I think one of the things we can conclude is that these old intuitions that were voiced by musicologists and linguists and that sounded a little crazy at first were actually correct. These were people that were hearing very subtle things in music that actually turned out to have a scientific basis. They were able to hear through the surface of the music into patterns that did reflect the native language. One thing we also have learned is that it's good to start small with just a couple of cultures if you're trying to study something that's cross-cultural and measure it, but it's good to develop a method that can be used to broaden the focus and look at other cultures and other time periods. That's what's happened with this work. This approach of using the NPVI to compare rhythm and speech and music has now been used by others to look at other cultures. For example, Rebecca McGowan and Andrea Levitt at Wellesley University looked at folk fiddling in Kentucky, Ireland, and France, and looked at archival recordings of fiddlers speaking and playing their instruments, and found that the rhythms with which they spoke were reflected in the rhythms of their fiddling. But there's lots of open questions and things that one could explore. For example, would this hold up in jazz? There's an intuition, Paul Berliner talks about this in his book, Thinking in Jazz, that there's some connection between jazz music and conversational rhythms. But this is a way you could actually study that. Do the solos of famous jazz musicians reflect the way they talk? What about classical musicians? When they play their instrument, are they imparting through their fingers, for example, the rhythms of their native language? Would a French pianist and an English pianist playing the same piece somehow express the rhythms of their native language and the nuances of their timing as they play? So I think the bigger idea is that once you have a new tool, a new way of measuring something, it opens up new questions that you can ask. And we've done that a little bit in our work. We've looked at how the rhythm of a culture's music changes over centuries of time using the NPVI equation. Finally, let's just talk briefly about what all this means from a cognitive standpoint for the brain. What does it mean that rhythm in speech can be reflected in music? Well, I think it tells us something about how our brains represent language. it's not just that we have a representation of the words and the grammar and the meanings of sounds in language. We also, at some level, seem to have a representation of the pure rhythm of language in our minds, because we can abstract it from the sound and then use it to create art. And I think that's an interesting thing. And it fits with this idea of a growing evidence that there's quite a few connections between the way we process music and the way we process language in the brain, more than people had suspected for a long time. And I talk about that a lot in my book called Music, Language, and the Brain. That's all I wanted to tell you about today, and I hope that you'll get a chance to maybe try out this for yourself. Using this equation is something that you can do if you have a computer and you have the ability to measure timing of sounds in speech and in music. You can do this science yourself, and I encourage you to try it. It's a fun way to explore the intersection between math, science, and music.